Hi, everyone. Thanks for the introduction, Sharia. As you said, my name's Ethan. I'm a hopefully soon to be graduated in approximately a year, but we'll see, PhD student at Cornell. And this is about securing smart contracts with information flow. So there are a few different ways that existing systems, there we go. There are a few different ways that existing systems tend to, okay. There are a few ways that existing systems tend to try to secure smart contracts. And broadly speaking, I want to put these into two different categories. So the first category is language-based solutions. And language-based solutions are really nice in that they provide what's called compositional guarantees. So this means that if you have two different contracts that are both written in that language and the language provides some guarantee, then we can put those two contracts together and create a larger application that's built from the combination of the two contracts. And we can be sure that they're going to cooperate safely so that that entire application is going to maintain the same guarantees that we wanted the original contracts to guarantee just because they're written in that language. Unfortunately, existing languages that support secure by construction smart contract development tend to assume everything in the system is written in that language. And so that means that if this application needs to interact with some third contract that's written in a different language that provides different guarantees, or is needs to interact with some legacy code that might not provide any meaningful guarantees at all, not only is that third contract potentially vulnerable, but its vulnerabilities can break the security of the entire system just simply by interacting in unexpected ways. The second type of tool is static analysis tools, these sort of standalone tools. These are explicitly designed to fix the problem I just described, where they have no assumptions about what other code is running in the system or what what sort of interaction might go on with regards to adversaries. So we can write one contract, we can check it, and we can have it safely interact with anything we want to, whether it be legacy code, whether it be some contract that hasn't been checked by the same or even any static analysis tool or something like that. Unfortunately, these tools tend to provide non-compositional guarantees, and they only consider individual contracts one at a time. And so that means that if we have two contracts that are both checked separately by the same tool, which most of these tools would require us to check them separately, we know that they're both individually safe, but they might not compose into a larger application that's safe. We might essentially lose the security that we were trying to maintain just because we plugged them together and they interacted in a sort of weird and unexpected way. And the work that I'm talking about here is trying to provide both types of security at the same time. We don't want to place any assumptions on what code your application is interacting with. It can be legacy code, it can be some sort of arbitrary, EVM bytecode that somebody put on the blockchain, sure, whatever. But we also want to say that if we have two contracts that have both been verified as being secure by our techniques, by our system, that you can safely plug them together and make sure that the combined application is still going to guarantee security. And just to take a step back and say, why is it really important and really difficult to get this type of guarantee? We really have to look no farther than April of this year, when a reentrancy attack exploited the interaction of two otherwise benign contracts and a third malicious contract, when $25 million worth of tokens from the Uniswap and Lendef.me exchanges were swiped through a somewhat complicated and tricky reentrancy attack that actually had been known about for about a year at that point. But April of this year is when somebody actually managed to exploit this. And our approach to identifying and eliminating this is that we view this sort of theft as an integrity violation. And what we want to do is we want to track the integrity of the code and data within a system so that we can prevent untrustworthy inputs from corrupting trustworthy state and getting us into a bad position. And to see a sort of an example of this that's a little easier to understand than what happened with Uniswap, we're going to look at a multi-contract bank. So this is somewhat similar to Uniswap in that it's got multiple contracts that need to trust each other and are interacting, but it's a bit simpler to explain. And the idea behind a multi-contract bank is that it's a single bank application. It's one application, but it's split across two contracts. And so we have these two bank contracts, and each of the bank contracts have, some pile of money. This is the collective of these two, of the balances of each of these is the total amount of money that's stored in the bank. Also, each of the contracts is going to store its own copy of the bank's account balance sheet. So maybe Alice has $50 in her account, Bob has $20 in his account. And while both contracts are storing a copy of this, it should be exactly the same. This is a copy of the entire balance sheet for the entire bank. So someone should be able to deposit money into one contract and pull money out of the other one, for example. So to see how this works, let's say that Bob comes in and he would like to withdraw some money from his account. So he asks the first contract, please send me $10. I'd like to withdraw $10. So hypothetically, let's see how the withdraw operation on this bank contract might work. First, it's going to check its local copy of the balance sheet. It doesn't want to have to go outside the contract. That's expensive. It takes a while. So it's going to check its local copy and say, yep, well, Bob's account, Bob has $20 in his account. He wants 10, so this is fine. We can send him $10. Then we know about, the sort of classic DAO style reentrancy attacks. So the first thing we're going to do at this point is we're going to decrease Bob's balance on the local balance sheet and say, well, okay, Bob now has $10 in his account, and then we send him his $10. Now, because of how Ethereum and other blockchain systems work, at this point, we sort of have to wait for Bob to return as we send him his $10. And what's supposed to happen is that Bob is going to return the money, and he's going to return from the function call, take the money, put it in his pocket. And then once that happens, we're going to go ahead and synchronize with the other bank so that it can update its balance sheet and know that Bob only has $10. And now the entire transaction can complete, and Bob has successfully withdrawn his $10. But let's say that Bob isn't actually behaving how he's supposed to. Bob's got a bit of an evil streak going on here, and he's got an idea. He's going to start by making the same request he did before. Same thing, please send me $10. Well, Bob has $10 in his account now, so we check that he's got $10. We decrease it to 0. We send him his $10. But instead of pocketing that money and returning, Bob is going to freeze this operation in some sense and pause it right here at step 3, where it's waiting for him to return. And now he's going to send the same withdraw call to the second contract and say, please withdraw $10. And that contract is running exactly the same code, so it's going to execute exactly the same steps. It's going to check the local copy of its balance sheet, but we haven't synchronized from the first call yet. So the local copy still says Bob has $10. So it says, okay, sure, you can withdraw $10. It'll decrease that down to 0. It'll send Bob his $10. Bob just got $20 out of this bank application when he was only supposed to have 10. And what happened here is that Bob essentially executed a reentrancy attack into the application, even though it was calling into a different contract. And the problem here is that he violated trust that the bank had implicitly placed in Bob through this withdraw code. The withdraw code had implicitly trusted Bob to return when it sent him $10, to pocket the money and return and not call into the other bank contract. But he'd violated that trust. And by violating that trust, he was able to extract extra money from the bank. So we would like to be able to track and understand where that trust exists and specify it and make it explicit so that we can make sure that it isn't violated. And we're going to do that using something called information flow control, or IFC. Some of you who have been to previous IC3 boot camps or retreats in the past may have heard me talk about information flow control at various different points in similar contexts. But the basic idea is that we want to label data and computation so that we can track how different inputs affect different outputs. And in particular, we want to make sure that trusted data within the system can't be corrupted by untrusted data. So the trusted data can influence the untrusted stuff. But if somebody I don't trust is supplying data, is telling me what to do, I shouldn't allow that to influence my trustworthy decisions and my trustworthy data. And one of the really nice things about information flow control is that we can check it with a type system. And checking it with a type system gets us a few nice properties. It tends to be very efficient. We can do it entirely statically, and it's completely compositional. So that's really nice. So let's see how we would apply just standard off-the-shelf IFC to this bank example. Well, the first thing we need to do is we need to tag all of our data and code with a trust level. So the bank is sort of, it needs to trust the money it's got, and it needs to trust its balance sheet. So we're probably going to tag sort of the balances and the money as trusted. The withdraw operation, we know who wrote the code, we know that it's supposed to work properly, and it needs to interact with these balance sheets and the money. It needs to change the balance sheets, it needs to send money, so we better mark that as trusted as well. But Bob might be trying to attack the system. We don't really know who Bob is or what he's doing, so we're going to mark Bob as untrusted. Now let's see how this actually works. There's a core rule in traditional IFC, off-the-shelf IFC systems, that says that untrusted parties, Bob, for example, cannot call into trusted code, because this would be an untrusted party making a decision about what to do with trusted code and trusted data, and that's dangerous according to the standard information flow rules. So this means that when Bob tries to withdraw money from the bank, we've got a couple options. Now, this isn't an attack here. This is just Bob saying, I would like to withdraw $10. The standard wants to get his money back. Our two options are, we can either have the withdraw code marked as trusted the way I have this shown on the slide right now, but then the standard IFC rule is going to stop this call from happening. It's going to block it because it's untrusted Bob trying to call into trusted code with withdraw. And the rule says that's not allowed. So now Bob can't withdraw money. It's not just that he can't attack, he can't actually get his money out of the bank. Another option would be, well, we want to make sure that Bob's allowed to call withdraw. So maybe we should mark withdraw, the code for withdraw, as untrusted. But if we do that, the same rule is going to tell us that untrusted code isn't allowed to modify trusted data. So the untrusted withdraw code can't modify the balance sheets, it can't send money, it can't do the things that it actually has to do to implement withdraw. And so it's actually entirely broken. So the problem here is that this doesn't work, right? We've sort of had two options, and both of them have totally broken the functionality of the bank. I suppose the bank is secure, but it's secure because it's broken. It doesn't do what we want. And so we're going to have to modify the IFC off the shelf a little bit. And the way we're going to do this is we're going to add something that we call trusted entry points. These aren't new, these have been used in other systems previously, but the idea behind a trusted entry point is that we want to allow untrusted users and untrusted code to call into trusted code, but only at very specific locations. And so we're going to mark the withdraw operation, the code, as trusted, the same way we did before, but we're also going to give it this extra little tag. We're going to say this is a trusted entry point. So now, even though Bob is untrusted, he can call into the trusted entry point and it will accept his call, and it can still modify the balances, it can still send him money, and we've got our functionality back. The bank is back to working. But some of you who are paying very close attention might notice a problem with this. The original reentrancy attack works again, exactly the same way it did before, because when Bob makes the reentrant call, it just goes into the trusted entry point, and it still breaks the bank. Bob still steals money. So you might think we didn't get anywhere, but don't worry, not all hope is lost. We've actually gotten a very long way here, because what we've done is we've identified critical code within the system. And we've identified that this withdraw operation is sort of critical code that we need to worry about, and we can actually use this to give a more formal definition of what reentrancy means. We can actually provide a precise definition of reentrancy so that we can then try to secure it. And the way we define reentrancy is that it's an execution stack that has two trusted operations separated by an untrusted one. So for example, we might have a withdraw operation on the stack that then called Bob to send him his money, and Bob then called withdraw without returning. That's two trusted withdraw operations with an untrusted Bob between them. This is reentrant. A non-reentrant execution, however, would be, say, if Bob called withdraw and withdraw calls the synchronize operation, which is a trusted operation on the other contract within the same application. And so now we have two trusted operations on the stack, but there's nothing separating them. So this is not reentrant. This is fine. And this definition doesn't actually tell us what security is. It's just defining reentrancy. But we can use reentrancy to then define the security condition we actually want. And that security condition is that reentrancy doesn't create bugs. We want to make sure that specifically that any behavior that we can exhibit through potentially reentrant executions is behavior that we could have exhibited anyway, right? And this is actually, if we look at the broken, buggy, multi-contract bank, this is violated, right? Bob, without executing without a reentrant call, Bob was only ever able to withdraw the amount of money that his balance sheet said he had. But with a reentrant call, Bob could withdraw more money than that. He could actually withdraw twice as much. And so based on this security definition, our bank was not secure. And that's good. That's exactly what we wanted. That means that this is actually telling us something meaningful. But I haven't told you how we actually achieve this yet. And the way we achieve it is using a reasonably straightforward locking mechanism in that we want to lock integrity levels. And in particular, when we enter one of these entry points, we want to lock the integrity that it granted. And so if we have this sort of trusted and untrusted thing, when Bob calls withdraw the first time, we go into an entry point and we grant integrity from untrusted to trusted. And so when we do that, we lock the trusted integrity level. And then what we want to do is we want to prohibit re-granting locked integrity. So you can give away integrity, so the bank can safely send money to Bob. And this is essentially all that's necessary at this point for the honest withdraw operation. If Bob is just behaving honestly, this is all that's needed, and the locking mechanism allows this to go through fine. However, if Bob tries to execute this reentrant attack, he's going to call another withdraw while the withdraw and the send are both on the stack, and it's going to try to re-grant the same integrity that was granted by the first withdraw, and we'll notice that that was already locked, and we'll block this call and disallow it from happening. And so now we've actually been able to prevent the attack. There are two different ways to do this locking. We can do it either statically or dynamically. And the reason I bring up this separation is that they have very different contours to them. First of all, for static locking, we can track the locks with a type system. And tracking the locks with a type system has a really nice property that there's no runtime cost whatsoever. Because we can just check everything at compile time, and if it works, if all of the locks are satisfied, we don't have to do anything at runtime. But it assumes all of the code in the system is well behaved, which is, as I mentioned at the beginning, one of the core things that we're trying to avoid here. Another option is that we could use dynamic locks at runtime. And when somebody enters one of these entry points, we can put a dynamic lock in place and we can check them all dynamically. This has a potentially high runtime cost, which is a little unfortunate, but it's nice in that it works with completely arbitrary code. And what we want here is we'd like to get the best of both worlds. And so we use both. And specifically, the way that we use both is that we have a type system that tracks the locks by default. So we're going to use this sort of static locking mechanism with no runtime cost by default. But instead of losing security if we call other code that might not respect these locks, that might do bad things, the type system just disallows code. It calls to this unknown code entirely. It's very restrictive, but it's safe. If you can't call something that might misbehave, it's not going to break your system. But we want to allow people to actually interact with unknown code. That was sort of the point. And so whenever a programmer wants to, they can request a dynamic lock. And that dynamic lock has runtime costs, but the programmer is now requesting it. And at that point, the type system becomes aware of the fact that the programmer has requested a dynamic lock. And so it releases it at the type level. It releases the static lock and allows the programmer to actually call into this potentially dangerous unknown code, knowing that there's a dynamic lock that will be checked to make sure that nothing bad happens at runtime. So to sum up what I've talked about here, we're designing a system that uses integrity-based locks with information flow control. It provides composable security guarantees, and still allows our secure contracts to safely interact with legacy code or unknown code. There's a few pieces of this that we're still working on right now. We're working on an implementation. We have a prototype type checker, and we're working on some slightly more permissive rules. Some of you may have noticed that in the multi-contract bank example, by switching a couple of lines and doing things in a different order, we didn't need to put dynamic locks in anywhere. We've actually got some somewhat complicated rules that will allow that to work statically. We're also working on proofs of security. That's actually what I've been doing for like the last week. We're really, really close to actually having proofs of security. And we're really interested in anything that people in this community think would be good in terms of helping with usability, in terms of how to actually get this out there. We want people to use these ideas and these techniques. And so with that, I'd like to thank everyone for listening, and I would be happy to take questions.
Thank you, Ethan. Yeah. Does anyone have any questions? I see one. I love the wallpaper, Ethan. That's one question.
Thanks.
It's great. I haven't ever seen somebody's, clothing match the wall.
Yeah, honestly, that part was kind of an accident, but I'll take it.
I think it's great. I think it's, it's really good to look at, but okay. I don't see any other questions in the chat. If anybody wants to talk, feel free to.
Andrew had a question. Downside of locks, settings where these are likely to be unsuitable, like too much contention or something. Yeah, so I think we're envisioning this in a setting, in a smart contract-like setting, where we really only have a single-threaded operation. And so these aren't locks in the standard concurrency sense, where they would block until the lock is released, because if you actually end up with something that has a blocking semantics, anytime the lock is used, it would create deadlock. And the whole point is for these to be non-reentrant locks. So we're sort of envisioning this in a single-threaded context, where if you attempt to take a lock that's already there, you actually just get an error that aborts the transaction.
Is there a setting where you would want that to be able to be used? I mean, it's not so much contention in terms of multiple threads, but it would be contention in terms of a potential workflow or usage of a contract that now is forbidden here, but there could be a plausible.
You mean something where you might have something that's sort of temporarily locked across multiple transactions and then gets unlocked later? That's a great question. I don't have an example offhand where you would want something like that, but I totally believe that one might exist. And if anybody has any ideas for what that might look like, I would love to talk to you offline about it.
Cool, thanks.
Okay, great. Let's thank Ethan again.